In this video, we're going to take what we learned in the last video, which focused on standard reduction potentials for half cells, and then we're going to look at what happens when we put two of these half cells together to make a cell. So this is basically how we're going to calculate the cell potential for a complete cell. So if we look at the cell that we've been talking about this entire time, the zinc solid plus copper 2 plus gives, this is aqueous, gives zinc 2 plus aqueous plus copper. And we have our half reaction. Zinc goes to zinc 2 plus 2 electrons. And we have our copper 2 plus 2 electrons goes to copper solid. Okay, so basically this has two half cells put together. We have a zinc half cell and we have a copper half cell. So we can go in the book and look up the values for these. So this is the cell. Now, if you go to your table for the standard reduction potentials for the half cells, you're going to find two numbers, and they're going to come as follows. So you're going to get, they're always going to be reductions. So you're going to get zinc 2 plus 2 electrons goes to zinc, and you're going to get copper 2 plus 2 electrons goes to copper. And the reduction potentials for these are going to be 0 plus 0.34 volts and minus 0.76 volts. So how do we combine all of this into a single framework in order to understand how to calculate this? So you have two options. Basically, what you have to know is that when we combine these together, the fields for the push and pull of electrons are going to combine, meaning the copper is going to be kind of pulling electrons toward it, and the zinc is going to be pushing electrons away from it at a certain amount. And that push and pull is going to add together to give us a single field from the anode to the cathode. Meaning as an electron moves from one place to the other, from the minus side to the plus side, it's going to get pushed with a certain force. So now the problem though is that the zinc is not, we can't just go straight across here and use the zinc, right? So that we can kind of see that the cell potential for this is going to be 0.34 volts, because that matches very nicely with the copper. These two are the same. The problem is what happens when you have a standard reduction potential and then you have an oxidation in your cell. Well, it turns out that when you flip it around, so let's just make a little note over here. So when you flip from a reduction to an oxidation, you can flip the sign, of E naught red. So what that basically means is that E ox is equal to minus E red. So in this case, if we were to apply this, we would say that we can take this, flip the sign, since we've flipped these two reactions with respect to each other, and we can say, well, then the cell potential for that guy is going to be 0.76. So the overall field is going to be the combination of those two, which is 1.10 volts. So what you can so what you can say for the cell potential then, the cell potential is the combined potentials for the oxidation and reduction half reactions. So we can say that E cell is equal to E red plus E ox. And that's exactly what we did here. So we flipped around the oxidation potential and we got 0.76 volts, and then that's how we get our cell potential. The problem though is that this can be a little complicated, because when you look up the sign from the table, to have to always be thinking, well, which one do I flip? That kind of doesn't make the most sense. So what I prefer to do is I prefer to say, well, let's think of this in terms of just reduction potentials. So in this case, we would have 0.34 plus 0.76 volts equals the E cell, which is the 1.10 volts. But what about in terms of What about in terms of just reduction potentials? So what about the cell potential from reduction potentials? So what we can basically say is, well, we can say, well, if E cell is equal to E red plus E ox, and we know that E ox is equal to minus E red for the anode. So this is for the, sorry guys. So this is for the anode. What we could say is, well, the E cell is going to equal the E of the cathode, E naught red of the cathode, minus E naught red of the anode. So because we're flipping the sign of the anode all the time, we can simply say that E cell is equal to the E naught reduction of the cathode minus the E naught reduction of the anode. And these values you can pull directly from the table. So you don't have to worry about changing the sign. So a little bit more simple way of doing this is basically to say that E cell is E of the cathode minus E of the anode. So that gives you a sense of what to do. And now we're going to actually look at a lecture problem where we start to work on this and look these values up from the chart. Okay, so here's a lecture problem where we're going to start working with standard cell potentials. So for the following, here's what we're going to start to do. So we have to first identify what is the anode and what is the cathode. So we have to go through a standard process here of kind of getting out information from what we're given. So in one case, in the first case, we're given a reaction, and in the second case, we're given a cell notation. So this is good because both examples will help us out. So in this case, we have to identify the anode, and we have to identify the cathode, and then we know what numbers to pull from the table. So the anode in this case is going to be the cadmium, because we have cadmium going to cadmium 2 plus 2 electrons. And then the cathode is going to be the silver, which is 2 silver plus 2 electrons goes to 2 silver. So now we have to look up the values for this. And this is actually an important thing to pay attention to, because you're going to notice that even though we double these values for the silver, we're going to continue to use the cell potential as is. So I'll explain why in just a second. So if you go to the table and you look up the cadmium half reaction, you're going to find out that the E naught for cadmium 2 plus 2 electrons goes to cadmium is equal to minus 0.4 volts. And if you look up the silver plus 1 electron gives silver. The E naught for this is going to equal plus 0.8 volts. So these come directly from the table. So now let's write our equation. E cell is equal to E of the cathode minus E of the anode. And so what we're going to get for E cell in this case is equal to the cathode, 0.80 volts, minus E of the anode, which is minus 0.40 volts, is going to give us an overall cell potential of 1.20 volts. Now let's talk about why we don't double the voltage when we have a 2 in the stoichiometry. So we do not double E naught. This is because we're talking about a field, okay? We're not talking about something, so fields are not dependent on stoichiometry. The stoichiometry will determine how many electrons are transferred, but it doesn't determine the intrinsic field, because basically when it boils down to it, even though the cadmium gives off 2 electrons and the silver only takes in 1, that electron, the average electron that's being transferred across the circuit is going from a cadmium to a silver. So the field is defined by the ions and their redox couples, and not necessarily by the number of ions that are taking place, that are being transported across. So the two that's involved in the silver is just accounting for the fact that there's a different number of electrons produced. But on average, as the electron is transported through that circuit, it still feels the same amount of field between the cadmium and the silver. So that's just important to keep in mind when you're doing these, because the beautiful thing is you don't even have to really worry about it. You just go and find the values on the table, plug them into the equation, and you've got an E cell. As long as you know this equation, you don't even have to flip the sign. So let's look at the next one. And this is a really good problem to look at, because what this one is in cell notation. So we have to recognize that this is going to be the anode from the cell notation, and that this is going to be the cathode from the cell notation. So we have aluminum going to aluminum 3 plus 3 electrons. And then our cathode is going to be iron 2 plus 2 electrons goes to iron solid. So if you go to the table, what you're going to find out from the table is when you have aluminum 3 plus 3 electrons gives aluminum, the E naught for that is equal to negative 1.66 volts. And then the one for iron, Fe2 plus 2 electrons gives Fe. E naught is going to equal minus 0.41 volts. So now you can take these numbers directly out of the table, as is. We don't have to do anything in terms of flipping. We don't have to worry about balancing this out or anything like that. We just put an E cell is going to equal the cathode, which is the iron, so minus 0.41 volts, minus a negative 1.66 volts. That takes care of the flipping for us. And then we get positive 1.25 volts. So that shows you how to calculate cell potentials given the structure of a voltaic cell, either through the equation or through the notation. So now that we know how to calculate cell potentials, the next thing we're going to do is we're going to look at how do cell potentials affect spontaneity in galvanic cells.